So far we've covered conducted emissions, which we can deal with by adding filters into design, CM chokes for power, or ferrite beads for signals. And then we talked about surge protection, which I normally deal with by adding a crowbar circuit to a switch mode power supply or adding more capacitance. Then we talked about electrostatic discharge, and we can protect against ESD with TVS diodes. Both surge and ESD form a part of immunity testing. Then the only remaining area is radiated emissions testing, which is quite often the most complex one, because it deals with emissions coming off the unit as the whole. And typically what I'm talking about here is good PCB layout design practices and good shielding. Once we finish drawing schematics, this is now time to do the PCB layout, right? Wrong. Actually, there is one more thing we need to consider before that, and that is shielding. And we need to make sure that we understand exactly at what points the connections are made to the shield on our circuit board. So, for example, those could be pillars that connect the chassis to the printed circuit board, or this could be connectors, such as a USB connector. And the rule of thumb is that you should only have one direct connection from the chassis to the printed circuit board in order to avoid ground loops. So let's say you've got a PCB with 4 pillars that connected to the chassis, which also has a USB connector on it. Where would be the right point to make this single connection? It would be at the USB connector, because this is where the highest frequency enters and leaves the printed circuit board. And this is the rule of thumb we should use. And there should be no more than one direct connection from PCB to the chassis, because otherwise we will have ground loops. Imagine that we have a shield connection here and a shield connection here. This has now creates a possibility of current flowing from one shield to another shield and going in different directions. So this is a ground loop, and this can create noise. Anyway, so we do not have this connection, and the only connection we've got, this one. So this is our shielding point. This is where we make direct connection to the shield. Then, what happens at our other points? Do we just leave them float? No, we do not. What we do is we provide a capacitor to ground at each point of this shield. Right? And the typical value I use is 10 nanofarad. What this makes sure is that we have a high frequency path for the current to flow, and that lowers the impedance of our ground plane because it is now connected to the chassis in multiple points. So that helps to dissipate ESD currents when we have electrostatic discharge applied to the unit into the chassis. So this is extremely important for ESD as well. Not only that, it also helps to maintain Faraday cage and contain all the high frequency emissions coming off this PCB. But we must make sure that we have a solid shield connection at the USB connector. So in order to improve that, we may want to add a gasket around the USB connector, which would look something like this. And this basically helps to make sure that we have a low impedance connection all around the USB connector directly to the chassis. And this is basically what we need to do. If you do not have USB, you may want to make this connection at another high frequency signal such as coaxial. And if you do not have any of this, then you simply use one of those connections and connect it directly to ground with either 0-ohm link or something similar. And one thing I didn't mention is that the capacitors must be at least 1.5 kilovolts rated, otherwise they will simply break when the ESD is applied. So this is also quite important to maintain isolation between shield and 0-volt plane. Then once we established all the chassis connection points, we should add this all to schematic and make sure it's documented accordingly so it doesn't raise any eyebrows and clear for everyone to see. Then we're finally ready to begin the PCB layout. And with PCB layout I always start with a layer stackup, because I want to make sure that every high frequency layer has an adjacent reference plate underneath it, and I want to have it no more than 4 mils apart. So it will have some sort of IC, maybe IMX microcontroller with 600 MHz clock frequency. Then directly under it we would want to have 0-volt plane, and the dielectric thickness is going to be no more than 4 mil, so less than. Then we may want to have a slightly thicker dielectric under it, maybe a 60 mil, so that we can have another plane which could be like a power plane, possibly. So 3V 3 for the core supply of the IMX MCU, and under it we will have another dielectric layer and a bottom layer where we may have another IC, maybe some DAC or anything. So this is obviously where we're gonna route some high frequency signals as well, so I will have the separation distance 4 mil or less. Again, very important, when we do change layers from top to bottom during routing, even though we want to avoid it, it is kinda necessary most of the time. I like to put in a capacitor at every point when this happens, which is called EMI stitching capacitor. So I'm just gonna write stitch. It is typically 10 nanofarad value. So what that does, it provides a direct path from one reference plane to another reference plane for the return current. And this is very important because it helps me to direct the current in the way I want it to go, and without this cap the return current will kind of be lost and it will find its path back some other way, but it will be completely unpredictable and it will screw up the performance of my PCB, so I don't want that. I will add this cap to make sure I know exactly where the current flows. And like I mentioned earlier, during PCB layout it is crucial to have separation distance between different blocks. So for example, if we have a DC-DC converter which does it at 5 amps, something 3V 3, and we also have a digital to analog converter in a system, I do not want to have those blocks close together because it will ruin the performance of my digital to analog converter if I have them next to each other. So I will put them quite significant distance apart, and by that I mean maybe over 100 millimeters or so, at least, so that the interference is minimized, and I will consider putting some shielding over the DC-DC converter if necessary. It is less of a concern when the frequency is so much higher than the frequency of conversion. For example, if we had an IMX MCU here, there is no problem placing it close to the DAC because 600 MHz is much higher than the frequency of conversion of digital to analog converter, so it's not gonna cause big issues. Having said that, you should avoid doing that if possible. If you have a lot of space on the PCB, just separate all those blocks far from one another, and that would be the best thing you can do. Finally, when you have board-to-board connections, such as for example flat foil connector, maybe 10 pin or something, and it's connected to another FFC on another PCB. Then first of all, we want to make sure that those foil connectors are located in a sensible positions to ensure that this connection is as short as possible and as direct as possible and doesn't go in some funny ways over some switch mode power supply or whatever, which will make it quite noisy and terrible. Then the other thing I like to do is I like to add 15 picofarad filtering caps on each signal line so that any external noise that might be induced into this cable will be filtered out, or at least lowered to the point where it doesn't cause any interference. Those capacitors can also be replaced for 1 mega ohm resistors, which will make sure that if the flat foil cable is not connected, it's not going to create an antenna situation. Finally, when assigning signals to connectors, make sure to follow 60 to 40 rule. And that is the ratio of signal to ground. So basically, on a 10-pin connector, we should have 6 signals and 4 ground pins. The last thing I'm gonna say about PCB layout today is that when we add a TVS diode for protection against ESD currents, we must make sure that we add them on the path of the signal and not on the other layer or connected with a separate trace or any other nonsense way of doing it, because otherwise it will compromise the effectiveness of this protection. So this is basically how you should do it, and you must also make sure that those paths are length matched before and after the TVS diode. And like I said before, those should be no more than 10 picofarad capacitance, because this is a high frequency trace and it will stop functioning if you put a big TVS on this. I will also take into consideration the impedance matching of all differential traces. So for USB we want to make sure that this is 90 ohm differential impedance matched, and I will use impedance calculator within Altium Designer or one of the external tools such as Saturn PCB Design Toolkit for doing that. And for all other clock traces, such as for example 24 MHz clock signal coming from a crystal oscillator, I will add a series resistor of the value between 20 to 47 ohm, which would be located directly on the output of the crystal oscillator, and this makes sure that the trace is 50 ohms impedance matched. That is a standard value for majority of circuits. The other thing you can do, you can add a Thevenin configuration like I talked about in the other video, where both resistors are 100 ohm, and this is effectively achieving the same result. This is typically not necessary if your trace length is quite small, so which in this case it will be, so that's not very good example here, but you would want to use that in, for example, audio clocks or something like that, especially if it goes a long way from one board to another. Sometimes you may want to add 50 picofarad capacitor as well here, like I've shown earlier, which will basically create an RC filter and will slow down the clock edges as well. Like I said in the other video, inevitably this adds jitter to the clock trace, and this might be a big problem for you. Now let's say you've done a pre-scan of radiated emissions in anechoic chamber and you are failing at, let's say, 24 MHz. So this kind of narrows it down to this trace, because this is your only 24 MHz signal in this system, let's say. What sort of things you can do to reduce this emission? So first of all, you can try increasing this resistance or increasing this capacitance. This will reduce the clock edges even more. and eventually it will allow you to pass the EMC, but by that time your jitter is going to be quite significant, so it can compromise the performance of your audio system or system in general. Another thing you can do is that you can replace this resistor for a ferrite bead, and you can calculate the impedance of the ferrite bead according to the frequency harmonics where you are failing the EMC test. This is a very common solution provided by test centers when customers ask them to find and solve radiated emissions problems. However, all the best solutions are always going to come from the source, and what I described just now is solving the problem from the end rather than from the source. So the better way of solving this would be through a plane, and you must make sure that you have a very low impedance 0-volt plane directly underneath all of this nonsense. So under the crystal oscillator, under the IC, and under the trace itself, then your return current will flow in the dielectric space between the trace and the 0-volt plane, and this distance must be very short. So if this is our current path from the X-style to the IC via this trace, then our return path will be something like this, and due to skin effect it will follow under the trace, directly under it and not over, and the majority of energy will be concentrated in the dielectric itself. So the current doesn't flow necessarily in the trace, but it flows in the dielectric most of the time, and you should watch Rick Hartley's video about it if you want to learn more. So the main conclusion I want to draw here is that you must always pay close attention to your return current paths, and you must think about it from the current path point of view. What is the shortest path and what is the lowest impedance path, and how can I minimize it as a designer, and so that I can make sure that I know exactly where all my currents are flowing on a printed circuit board. This is really what we're aiming for, and not adding some ferrite beads or gigantic resistors into the path of the signal, because even though that gives us the result we want, it is not the way to do it, if you know what I mean. So finally, after I've completed the PCB layout, I will also think about all external connections that are made to and from this PCB, which may be made via USB cables or XLR cables and stuff like that. If this is a USB cable, is it 360 degrees shielded? I have made a video about that, and majority of cables in the market are not 360 degrees shielded, and this causes a lot of issues when we ship this cable with the product. So it should look something like that, where we have cable pairs inside the cable and we have a continuous 360 degrees shield around them. And to check that this is true, I have not found a better way of doing it rather than to open up the cable and see for myself, and I have talked about this before. Then you must also make sure that the metal enclosure around your printed circuit board has paint removed at all points where it makes connection with itself or the circuit board. Otherwise, it will not function as a Faraday cage and it will fail in improving your immunity and containing the EMI sources. To amplify the connection, you can also add a conductive gasket between different pieces of enclosure as well. Then to test for that, I always take out a multimeter and I make sure that I have a buzzing connection between different metalwork points and the PCB, and if it doesn't buzz, then it's as good as no shield at all. So to summarize, here's my PCB design for electromagnetic compatibility workflow. The first step is block diagram, where I identify all sources of potential EMI and write out the center frequency for each one of them. The second step is a schematic capture, where I place ferrites and CM chokes on every power supply, and I add all necessary precautions identified from block diagrams. The third step is identifying chassis connections and making sure that we have only one direct connection from the PCB to chassis, and we define the exact location of this point on the schematic. After all this, the fourth step is the PCB layout itself, where I apply all the best design practices that I just described. And finally, I check for cables or any other external parts that could be related to my product and which can still fail the radiated emissions test. So I hope you found this video helpful and insightful. As always, please like and subscribe, and let me know if you have any suggestions or comments about what I've covered here and what you would like me to cover in more detail in future videos. I will be releasing more EMC related videos on this channel very soon. So bye for now, and I'll see you shortly.